Hey everybody, so today we're going to take a look at creating ramps of values so that we can do fade in, fade out, move objects on the screen, change any value over time. This is of course very important in all time-based media, and there's a lot of ways, a lot of objects we can use to get changes over time in Max. We're going to look at a few of them today. So let's start with a practical example of something that we might want to do, for instance, fading out sound and fading out video. So in terms of fading out sound, we already have a way to create a smooth fade with a live.gain. We have the interp attribute, which from the list is called ramp time. This allows us to say, for instance, we always want the audio to fade over 2 seconds. So if I send a message of 0 to my live.gain, it will fade in over 2 seconds. When I send a message of -70, it fades out over 2 seconds over this interp time. And the problem here is that this little arrow doesn't show us the fade time. It jumps to the new location, and the sound will fade, but graphically we don't have visual feedback on that fade, so that's a problem that we can solve today. So I'm going to change this interp time back down to a short value, back down to 20 milliseconds, so that we can control this fade from another source. So let's say we want the fade in and fade out to happen in response to a keystroke. So we'll create a key object. ITOA will convert it from ASCII code into symbols that we can see. There's my keys coming in. And I'll use A to fade in and S to fade out. So when I hit the A key, I'm going to get a bang there. And when I hit the S key, I will get a bang here. Okay, so how do I translate these impulses into a ramp of values that are going to cause my audio to fade and my video to fade? And the object for that is line. And line takes an argument that sets its starting value and also determines whether it's going to output floating point values or integers. So let's just give it an argument of 1 floating point. That means it's going to start from 1, and also it's going to give us floating point output. And line takes a message, a 2-element list, that is destination value, followed by time to reach destination value, say 3 seconds. So this line, if we put a floating point number box here to see what it's doing, is going to go from its current value, which is 1, down to 0 over 3 seconds. And we can see it goes down there. And if we want it to ramp back up over 2 seconds, we have a message that's 1 floating point space 2000, telling the line to ramp back to a value of 1 over 2 seconds. And there's that value changing. Let's apply that to fading our video to black. And fade to black is a function of the color attribute of the layer. So we'll choose color here, and then as we've looked at before, when you're working with color, it's a good idea to set your display mode to multi-number float so that you can see the actual values that are here. And we don't want to change the transparency, we just want to fade to black. So we're going to fade red, green, and blue from 1 down to 0. We'll use a pack object for that, pack 3 floating point numbers, and a 1 into a list. And we're using a 1 here because that's our transparency value, which we don't want to change. And I'll take the output of my line and use it to create changes in the first 3 elements of the list. And now my video will fade out over 3 seconds and fade back in over 2 seconds. And if you're not entirely clear on this pack object, you want to spend a little bit of time with it, work with it, play with it, because this is an important object that's going to keep showing up, and you want to fully understand how it works and what it's doing. You can use a message box to help show you what this pack is putting out. It's taking our value from line and placing it into the first 3 elements of a 4-element list, and leaving the 4th element as a 1. So watch what it does in the message box. Creates a continuously changing list of values that is sent to the color attribute. And of course we can easily connect this to our buttons. We want our A to be our fade in and our S to be our fade out. And now we've got that mapped to our keyboard. When I hit A, it fades in. When I hit S, it fades out. And to apply these same fades to the sound without using the interp, we can use a scale object and say we want the values between 0 and 1 to scale to the values that live.gain wants, which is -70 for silence and 0 for full volume. And whenever you're using scale, I strongly recommend that you size the scale so that the values appear on 2 lines. You see your input values on the top line, your output values on the bottom line. This just makes the scale a lot easier to read. So we can take this same output of our line, pass it into the live.gain, and now as we fade the sound in, we're also going to see this arrow fading in along with it. So we're fading in with the A key, and fading out with the S key. And if I want my fade times to be different between the sound and the image, I can just create another line object specifically for the sound. And for instance, have the sound fade in over 8 seconds and fade out over 5 seconds, while the video is fading in over 2 seconds and fading out over 2 seconds. So when I hit the A key, I'm going to get an 8-second sound fade and a 2-second video fade. And the S key gives me a 5-second sound fade out, a 2-second video fade out. So that's the line object. And of course, we can also use pack to create our lists. We're creating a list that's a float and an integer, a float representing the destination value of the line, the integer representing the amount of time to get there. So this allows us to do things like use a toggle and dynamically change our fade time. So here's my 2-second fade in of video when I click the toggle. And then I can change this value, for instance with a message. So if I want a 1-second fade out, I select 1 second and then fade. It's a 1-second fade. If I want a 5-second fade in, I select 5. It sets the right inlet of my pack. Click the toggle, and now it's fading in over 5 seconds. And if I want a key to handle both my fade in and my fade out, I can just connect it to that. So now my S key is fading in and out my video. When I hit S, it fades out. When I hit S again, it fades back in. And of course, can do the same thing here. So I can set a time and hit A to fade my sound in, A again to fade my sound out, S to fade my video out, S to fade my video back in. And again, toggle isn't our only option here. We could, for instance, have several brightnesses that we want to fade between. Fade to black, fade to dim, and fade in. There's my fade to black, fade up to 50% brightness, then fade the rest of the way up to brightness. So these allow you to make smooth transitions in terms of sound fades, in terms of video fades, and also, of course, in terms of video tint. If I didn't attach this pack to all 3 points here, this would become a tint fade, where I'm fading the redness in and out of the video, because I'm not affecting the green and the blue. Or I could do the red and the green and leave the blue alone. And of course it works just as well for transparency, except I need to change this from PACK to PAK, because nothing's coming in this left inlet to trigger it. So in this case I would actually do pack 1, 1, 1, since I want those to stay, values of 1, and F for the floating point value that's coming in the 4th inlet. And now my video is going to become transparent. And we can see that it's transparent if we add another layer. Fade my video in. As my video becomes transparent, it reveals the layer underneath. So that's the line object, and you can use that for a lot of your time-based transitions. Let's encapsulate that and take a look at a couple other options. So the next thing we want to take a look at is jit.anim.drive, because jit.anim.drive is what allows us to move layers and other visual objects that we haven't learned about yet around on the screen. jit.anim.drive, and right now we're connecting it to a jit.gl.layer because that's all we know. There are many other visual things, both two-dimensional and three-dimensional, that can be placed into a jit.world. And let's get an image for this. Send it to our layer. And there's my image. And this is an image with a transparent background, so it doesn't come in with the square around it. The square is still there, but the square is transparent. And you can take a look on Mac's Tips and Tricks for how to find images with transparent backgrounds, how to make images into images with transparent backgrounds. So the jit.anim.drive just gives us some very simple commands that are, as most commands in Macs, are a list. For instance, the move to message. Move to, and then 3 numbers representing the X, Y, and Z coordinates to move to. And jit.gl.layer doesn't have a Z, it doesn't have a depth, so we're only going to be concerned with the X and Y. So if I want to move it to the left, I can say move to minus 0.5, 0, 0, and then the time of the move in seconds. So 2.5 second move. And note how I'm formatting this. Move to X, Y, Z, and then on the second line of the message, I'm putting the time. It's much easier to read than this. It's hard to visually quickly pull apart what's going on. But just by making it a two-line message box, we see move to the place where we're moving to, and then on line 2 is the amount of time it's going to take. I just send that message to the jit.anim.drive that's connected to the relevant jit.gl.layer, and it moves to that new location. And -1 is the left edge of the screen, 1 is the right edge of the screen. Similarly with the Y axis, if I move it to -0.5, -0.5, negative values will move it down, where -1 is the bottom edge of the screen and 1 is the top edge of the screen. So if we want this to move around in a couple of different ways, just create a couple of move to messages. Move it a little quicker, 1.5 seconds. And there it moves to 1, which is the upper right-hand corner of the screen. And now over 2.5 seconds, it moves back down to its left position. Another message we have is scaleto. And again, it's the same format. It's X scale, Y scale, Z scale, which doesn't matter in terms of a jit.gl.layer, and then a time in seconds that we're going to scale. And again, I recommend doing this as a two-line message so we can see time on its own line. That's connected to the jit.anim.drive, and over 4 seconds, it will shrink down to half size. And if we want to restore the scale, or actually let's try making an oval here. Scale to 1 width, half height over 2 seconds. And now I have an oval, and when I scale it back here, it's going to return to a circle, and my move tos can move it around the screen. There is also a rotate to. However, rotate to is a little bit different, and we're going to need to use a pack for rotate to. Rotation can be expressed in a number of different ways, and in this particular case, it's being expressed as a quaternion, which is not a human readable form of rotation, but it's a very useful form of rotation for the computer. Our usual sense of rotation, of roll, pitch, and yaw, or X, Y, and Z rotation, is useful and intuitive. It also creates a problem called gimbal lock, where there are ambiguous rotations that it's not clear whether the object is upside down or right side up. And there's an alternative 4-value form of rotation called a quaternion, which is used by rotate to avoid the gimbal lock problem. So we need 4 floating point values for the rotation quaternion, plus a 5th floating point value for time. And because these rotational values are not human readable, we don't need to interact with them. There's an object called jit.Euler to quat, which is going to convert our normal XYZ rotations into quaternions. And this is going to go into the second inlet of the pack, because the first element of this list is the word rotate to. And then the next 4 values are being supplied by this jit.Euler to quat. And then our time is coming in here in the rightmost inlet as a float in seconds. So I'll do a 5-second rotation. And then to specify our rotation, now we can think in X, Y, Z degrees. So if I wanted to rotate around the Z axis 180 degrees, I can just say 0, 0, 180 into the jit.Euler to quat. I've already put in my 5, so let's move this back to where we can see it. and rotate it. And there, over 5 seconds, it's going to rotate to 180 degrees. And if I want to rotate it back, it's rotating back to 0 over 5 seconds. And again, this is another one of those usages of pack where if it's not clear to you what's happening here, if it's not clear to you why we're using the pack object or what the pack object is doing, stop the tutorial and work on pack a little bit, play with it, do some experiments with it, try to gain an understanding of the pack object, because it is pretty fundamental. We need to use it a lot. What's happening here is we need a message that is a list beginning with the word rotate to, followed by 5 values. And we know that the rightmost value is time in seconds. And we know that we need to express these 4 values as a quaternion rotation. So we're using jit.Euler-to-Quat to turn our common sense rotations into quaternion rotations. So when I initiate the rotation, we see that it formats a message for us. The word rotate to, followed by a 4-element list specifying rotation, followed by our time in seconds. So pack is a formatting object. It's taking the information and putting it into a single list in a format that an object wants, in a format that an object is going to understand. And of course, it can be used with these as well. In the case of scaleto, it's only a 4-element list, where this is time, this is X scale, this is Y scale, and actually our third value is always going to be 0 because there is no Z scale. And because this is a PAK pack with no C, anytime I send any of these values, it will format and send the message. So for instance, if I try to type in my time here, watch what happens. It shrinks to 0, 0, even though that wasn't necessarily my intent. And then if I put in values here, it automatically comes back. Now that may be a problem, so we can use PACK here. The problem is there's nothing coming into the left inlet to trigger the list, so no matter what I do here, this pack is not going to give me any output. So I can just use a button in the left inlet to trigger it. So over 3 seconds, I want to scale to a width of 2 and a height of 0.5, and then button to trigger. And if I want this to be interactive on my X, I can simply have X press the button for me. So over 2 seconds, I want to scale to 1 by 1. And as soon as I enter that 1 is set in the message, and it's also hitting this button, which triggers the output of the pack. And again, if this is not clear to you, if this is not working, stop and take the time with pack and study pack, because it is worth looking at. And if you don't find it useful to use the right inlet of the message box, or if you just want additional information, you always have the print object, which will print what it receives in the max window, so that you can really study what's happening here. Like I put in 3 seconds, nothing comes out of the pack. I'm scaling to 0.5, and then when I set my X, aha, at that moment, the message is formatted and sent out, and we can see it printed here. The final message is scaleto 0.5.503. So those are some of the features of the jit.anim.drive. One other thing that I'll add here is there is an easing function that we can apply to the jit.anim.drive easing function that allows us to either do a linear change, which is what we've been seeing so far, or to apply some easing, like a quadratic curve, and look at the difference. Starts slow, picks up speed, and then slows down at the end. And a more extreme version of that is a cubic curve. And that's useful for animation. You don't always want that linear movement from place to place. Sometimes it's nice for it to have a little feel to it as it moves. So I'll encapsulate this. And we'll look at one more type of transition that's specifically useful for sound. So here's a sound, and we want it to follow a volume shape over time. And there's a very useful object for that called function. And what function does is it allows us to draw the shape of these volume transitions. And we can use this visually as well, but I'm going to show it just in the context of sound for right now. So the sound would fade in, then quickly fade down, then fade back up, fade down again, and then fade all the way up. And the way we get this to work is by using a new outlet of our playlist tilde object, which is the sync output here, the third outlet. And so what this sync output gives us is the playback position within the sound, where 1 is the beginning of the sound and 2, or 1.99999, is the end of the sound. So if we connect a patch cord there, we say, wait a second, that's an audio patch cord, that's sound. Why is sound coming out of this outlet if it's giving us a number that represents playback position? Well, we're going to see this more and more in Macs. Often when we're dealing with sound, our numbers are going to be represented on an audio patch cord because the time resolution of an audio patch cord is vastly finer than the time resolution of a regular patch cord. On a regular patch cord, we're getting a resolution of about 5 milliseconds, 3 to 5 milliseconds per message, whereas on an audio patch cord, we're getting a resolution of 48,000 samples per second, 48,000 individual numbers per second. But for our purposes, we don't need that level of accuracy. So what we need here is a new object called snapshot, which will simply convert this number that's encoded as audio into a regular floating point number. And the argument, 20, tells us how often that conversion is going to happen. Every 20 milliseconds, we're going to get this position value sent to us as a floating point number. So take a look when I play the sound. It's going to start at 1. It's going to go to 2. So we can think of this as percentage, playback percentage. That's 25% through the sound. Here comes 50% through the sound. That's 50%. To the end of the sound, and when it loops, this is going to drop back down to 1.000. So it's giving us a value that then we can use to drive this function. And in order to do that, we need to do some scaling. We know that the value coming out here is between 1 and 2. So we're scaling values from 1 to 2, and those values are going to be scaled to 0 to 1,000. Why 1000? Because the default domain of a function object, if we go to the inspector, the default domain of the function object is 1000. We can change this, but if we just want to use the function object without having to make any modifications to it, we can simply respect its default domain of 1000, where this is 0 and that's 1000. So when this sound begins, this function is going to start outputting the value all the way at the left, and it will output all the values continuously until it gets to its rightmost edge, which is 1000. And we can see that here. Right, there's our level coming up. Now it's dropping back down, coming back up. Now it's a little bit hard to see in a number box. So there's a nice object called multislider, and multislider will show us this value as a moving bar. And if we want to get the multislider working even a little bit better, go to its inspector and select slider style bar and set its range to 0 to 1. And now we'll see what's happening on this function represented by the position of the slider. And if we want this to be translated into the volume fader position here, that's just another scale. We're scaling values from 0 to 1 to the values that live.gain wants, which is minus 70 to 0. And this is interactive, so we can make changes to this. You can shift click a point to remove it. Click a point to adjust it. And we can see that this multislider and this arrow are moving in the same pattern now. So in this case, we don't need the multislider, but if we were, for instance, using this to control brightness or to control color or to control some other aspect, it might be useful to have that multislider just so we have a visual output. So what's a little bit difficult about this, and let me just stop this for a moment, is that our function is down here and our sound is up here. So if we want things to be happening at particular moments in the sound, visually it's a little bit hard to get things to line up. And so here's something I'm going to introduce, which is very common in Macs, and we do it all the time in a lot of different contexts. We just stick one thing on top of another thing and line it up. And you say, well, that's not very useful because now we can't see the waveform. So if we click on this function, go to its inspector, and change its background color to transparent, and we'll change its foreground color to something really visible like red. And if we go to our playlist tilde inspector and turn off show file name, now we're getting a pretty nice interactive control. And you see I can refine my size of my function here so that that first red dot lines up right at the beginning of the sound. And while this might strike you as a bit odd, it's actually quite an elegant solution to creating layered user interfaces without needing to develop a separate interface building part of Max. It does get a little bit hard to read because these cables are going to an essentially invisible object that's sitting on top of another object. So it does, take a little bit of familiarity with Max to navigate this well, but it is quite useful. And another thing that's quite common is to line up objects so that they give you visual feedback in a place that's useful to you. So even though we are seeing this little arrow going up and down, it might be nice to have the visual feedback here, particularly if we change the color of it. Change that slider color to red to make it nice and visible. It might be useful in a performance setting to have all this visual feedback gathered in one place. And we've looked at the meter object as well. Which again, we could install a meter here and have it report the live sound level of this track. Okay, so those are a few ways to create movement, create shapes over time in Max. We can expand upon them a great deal more because, we are dealing in the realm of performance, and performance is a time-based medium. So there's a lot in Max that deals with time. But interestingly and nicely, it doesn't make decisions about how we're going to deal with time. Are we dealing in linear time? Are we dealing in cyclical time? Are we dealing in synchronous time, asynchronous time? Are we dealing in extremely short time frames, extremely long time frames? So before we close, I just want to address that issue very quickly to make it maybe a little bit clearer what I mean by Max's lack of assumptions. Because we've seen the clocker object. And the clocker object tells us the elapsed time in milliseconds since it was started. And if we want to see this in seconds, we can simply divide by 1,000. And now we're seeing seconds elapsed here. And if we want to see in minutes, divide by 60, and now we're seeing elapsed minutes. And if we want to see hours, divide by 60 again, and now we're seeing hours. And we can keep going. So here's time elapsed in days. And here's time elapsed in years. Right, so we're getting a very, very large potential time scale here. Much wider than you're going to get in any pre-made software tool. Adobe Premiere is not going to assume that your piece has a duration of 20 hours or 2 days or a month. And Max doesn't care. Max is agnostic. If you want something to happen after 1 day has elapsed, there we go. That toggle is going to become a 1 when this day counter passes 1 day. And probably what you're going to want here is a change object, because we only want that 1 to be sent when this transition is made, when it goes from being less than 1 day to greater than 1 day. So there is a limit to this. There is a highest number that Max can represent, and it is this number. So when this many milliseconds have elapsed, Max is going to actually stop counting properly. It's going to start counting backwards. So let's just check this value out and see how long it is. It is 292 million years. So you cannot really make a piece that exceeds 292 million years in length if you're using a clocker counting in milliseconds. So the limits, this is something I talked about in the previous video, you're not really going to hit the limits of the software. The computer will break down and crash and become unusable and become obsolete, and we won't even be using this sort of technology long before we've hit the limits of Max's time scale.